it's Jack here again. I hope you guys enjoyed what's been offered so far. This is going to be our last part of our lecture, and I'm going to teach you guys some stuff about force on a dam. So, quick review about a core physics concept is force equals mass times acceleration. So, we all know that one of the good example is force of gravity, which equals mass times gravitational acceleration equals 9.8 meters per second squared. And now we also know that mass equals volumes times density, which we learned in the last part. Um, and we can also know that from the units involved, which for volume is meters cubed, and density is kilograms per meters cubed. And when we time them together, we get mass in kilos or grams or whatever the unit is. And knowing both of that, we could rewrite our force function equals volume times density times little g, which we're going to focus on because we're on Earth, obviously. Now we also know that volume equals area times height, which we can also see from the units, area being meters squared times meters equals meters cubed, which is going to be the unit for volume. And tying that into our updated function, the force function is going to turn into area times height times density times little g, which we can write in terms of A times h times p times g. However, this is only true for a consistent area and height. And since we know the density doesn't change in this situation, as well as the gravitational acceleration. So, just like any other concept we talked about in this course, we would want to break down the really large, big changing parts and make it into like a stationary one so we can use our calculus techniques. So in this part, there's two things that are changing. One is the height, and second is the area. More specifically, it's the width of the shape that is changing, but we're going to focus on the height first. So the height is always going to be the top or the height of the water minus y. That is because at the top of the water, the height is going to be 0 because there's going to be no pressure, and at the bottom is going to be the largest since it is, well, at the bottom, right? And the second one is going to be, the second thing that's changing is going to be the width of the dam, and as we can see on the graph on the right, uh, the width of the dam towards the bottom is smaller while the width is larger on the top. So we're going to have to make up a function in terms of y to measure the width, and then times that by height, which is going to be delta y to get our area in order to calculate the area. We're not going to let you guys get the specifics of the area, the width function right now. We're going to introduce that more in our example, so we don't want to confuse you and make it more hands-on. So putting that all together, for each slice or each thin part of the dam, we're going to have Fk, which is going to be P times G times times A minus YK star, which is the height of that slice, and times the width of the slice times the height of that slice, which both of them makes up the area. Great. So that's just for one slice, and we all know if you want to get the mass or the force on the entire thing, we're just gonna have to add them all together and decrease the width and increase the number of slices. And after all of that, we're gonna get a definite integral of p times g times the height times the area, and the range is gonna go from 0 to a. However, we're going to talk about some few exceptions, but we're just going to dive into the example 6 right now. So if you have the book, please follow along, and the example goes as follows. A large vertical dam in the shape of a symmetric trapezoid has a height of 30 meters, a width of 20 meters at its base, and width of 40 meters at the top. What is the total force on the face of the dam when the reservoir is full? So when the reservoir is full, the water level is actually at 30 meters, which is equal to the highest point of the dam. So, as we introduced, we would definitely want to calculate one, which is the height of the strips. Uh, as we can see, it's going to be really easy here, since the highest height of the water is going to be 30. Uh, the height is always going to be 30 minus y. So there we go. And now it's the width part that I kind of skipped. That's easy because I feel like giving you guys a problem will help you guys understand a lot better. And looking at the right side of shape, we can see there's a line, and if we want to get the width of this shape, we will want to get the x value of the line as y changes. So looking at the coordinates, since it's a line, we can really easily get this function, and we got y equals 3x minus 30, and if we inverse that, make it in terms of y, it's going to be 1/3 of y plus 30. And however, doing that, we're only going to get half the width since we're only calculating from y equals 0 to the function, and thus we need to the true width of the shape is going to be 2 times the function, and we are going to get 2/3 times y plus 30. Now we have both the height and the width function. We're going to plug it in to the master function that we got earlier, and f is going to be the integral of p times g times 30 minus y times 2/3 of y plus 30 from a range of 0 to 30. And I'm pretty sure the integral is going to be pretty easy for you guys. So guys, now that we went through example 6, I want to turn your attention to exercise number 51. If you have your books, please follow along. If not, this is a quick little excerpt on the left hand side. And yeah, I'll give you guys a few minutes. When you're ready, please click